On the morning of June 4, 1996, the humidity in Kourou, French Guiana, was suffocating. But inside the Jupiter Control Center, the air was freezing cold, conditioned to protect the millions of dollars of electronics that lined the walls. Hundreds of the world's most brilliant engineers, scientists, and politicians were gathered to witness the birth of a new era. On the launch pad stood the Ariane 5. This wasn't just a rocket. It was a statement. It was Europe's declaration of independence in the space race, a investment designed to secure the continent's dominance in the commercial satellite market for the 21st century. Strapped inside the nose cone were 4 distinct satellites for the cluster mission, a scientific endeavor worth another $500 million, designed to map the Earth's magnetosphere in 3D. The Ariane 5 was a monster of efficiency. It was heavier, stronger, and significantly faster than its predecessor, the reliable workhorse known as Ariane. Every calculation, every bolt, every line of fuel had been optimized to deliver maximum payload at minimum cost. The countdown hit 0. The main Vulcan engine roared to life, followed milliseconds later by the solid rocket boosters. The ground shook. The rocket cleared the tower, climbing perfectly into the tropical sky. The telemetry screens in the control room showed all green lights. Trajectory, nominal. Velocity, nominal. Attitude, nominal. For 36 seconds. It was a textbook launch. The engineers allowed themselves to breathe. Some even began to smile. The hard part was supposed to be over. And then, at T+37 seconds, the unthinkable happened. Without any warning, without any external impact, the rocket violently swerved. The nozzles of the main engines and the boosters suddenly swiveled to their mechanical stops. The rocket turned 90 degrees horizontal while traveling at supersonic speeds. The aerodynamic forces, akin to hitting a brick wall at Mach 1, instantly ripped the boosters from the main stage. The onboard computer detected the structural disintegration and triggered the auto-destruct sequence in a fraction of a second. 10 years of European engineering and $7 billion of investment were transformed into a cloud of burning debris raining down over the mangrove swamps. There was silence in the control room, not the silence of peace, but the silence of absolute shock. There had been no engine failure, no fuel leak, no terrorist sabotage. The hardware had performed flawlessly. The machine was perfect. What failed was the mind of the machine. The Ariane 5 was murdered by its own brain. It was killed by a software bug so elementary, so textbook, that it is now taught in Computer Science 101 classes as a warning to every first-year student. It was killed by an integer overflow. To understand the magnitude of this error, we have to peel back the layers of abstraction and look at how computers actually store numbers. We tend to think of software as magic, but at the hardware level, it is just buck. But the code needed to convert this value into a 16-bit signed integer. Think of this as a shot glass. A 16-bit signed integer can only hold numbers between minus 32,768 and plus 32,767. That is the hard physical limit of the memory space. If you try to put the number 32,768 into that space, it doesn't fit. The binary representation flips. The computer panics. On the Ariane 4, the previous rocket, this conversion was safe. The Ariane 4 was a smaller, slower vehicle. Its horizontal velocity during the first minute of flight never physically reached a value high enough to overflow that 16-bit bucket. The math was protected by the physics of the rocket itself. It was impossible to generate a number larger than 32,767. So, the engineers, in their infinite wisdom, decided to reuse this code for the Ariane 5. They copied and pasted the software module from the old rocket to the new rocket. It saved Chimie. It saved money. It was proven technology. But they forgot one crucial detail. The Ariane 5 was a beast. It had a completely different flight profile. It accelerated much faster. In a normal computer, an unhandled exception causes the program to crash. You get a blue screen of death, or your app closes. You restart it, and you move on. But this was a real-time control system flying a bomb. When the inertial reference system crashed, it did exactly what it was programmed to do. It shut down its own processor and dumped a diagnostic debug pattern into the data bus. It basically said, "I am dead, here is why," and sent a stream of error data to the main flight computer. Here is the tragedy. The main flight computer didn't know the inertial system had died. It was expecting flight data coordinates, angles, velocity. Instead, it received the diagnostic error pattern. And by a cruel twist of fate, that error pattern looked like valid flight data. Specifically, it looked like data indicating the rocket was drifting wildly off course. The main computer panicked. It thought, "We are 90 degrees off course. Correct immediately." It sent a command to the engines to swivel hard to the side to fix a drift that didn't exist. The rocket obeyed. It turned into the wind stream, broke apart, and died. The investigation board, led by Jacques-Louis Lyons, produced a report that should be mandatory reading for every engineer on Earth. They didn't blame a single programmer. They didn't fire the guy who wrote the line int 16 equals float 64. They blamed the culture. They blamed the process. They uncovered a series of decisions that individually seemed rational, but together were fatal. The most painful revelation was that the piece of code that crashed the rocket was even needed for the flight. Its only purpose was to align the inertial platform before launch. Once the rocket leaves the ground, that calculation serves zero purpose. It is useless data. However, the engineers had decided to leave that function running for 40 seconds after lift. Why? To make it easier to restart the system quickly if the launch was paused at the last second. It was a convenience feature for the ground crew. A feature designed to save maybe 45 minutes of reset time on the ground ended up destroying the entire mission in the air. The rocket was killed by dead code. Furthermore, they found that the engineers had actively chosen not to protect that specific variable. In Ada, you can write code to handle overflows gracefully. You can say, "If this number is too big, just use the maximum value and keep going." The engineers had done this for 7 other variables in the same module. But for 4 variables, including the horizontal bias, they left the protection off. Why? Because of efficiency. In the 1990s, CPU power was limited. Every line of error-checking code consumes processor cycles. The engineers did a risk analysis for the Ariane 4 and concluded that since it was physically impossible for that variable to overflow, they shouldn't waste precious CPU power checking it. They optimized for performance and sacrificed safety. That optimization, valid in 1985, was a death sentence in 1996. This is the concept of legacy code biting back. We often treat software like a physical component. If a carburetor works on a 1990 Ford, it should work on a 1995 Ford. But software isn't a carburetor. Software is a set of assumptions about reality frozen in logic. When you change the reality when you put the software in a faster rocket, a cloud server with more traffic, or a financial system with higher frequency, trading, the old assumptions shatter. The code didn't change, but the context did. And context is everything. This disaster cost the European Space Agency $370 million in immediate hardware loss. But the indirect costs of delays to the commercial program, the loss of scientific data, the blow to reputation were in the billions. It forced a complete overhaul of how aerospace software is tested. It ended the era of "it works on my machine" in high-stakes engineering. But why does this matter to you? You aren't building rockets. You're probably building web apps, or data pipelines, or mobile games. Who cares about integer overflows in 2024? You should care, because the same mindset that destroyed the Ariane 5 is rampant in the modern tech industry. We are living in the golden age of copy-paste engineering. We grab libraries from NPM or PyPI without auditing them. We copy snippets from Stack Overflow or ask ChatGPT to write functions for us. We glue together massive, complex systems using code we didn't write and don't fully understand. Look at the CrowdStrike outage in 2024. A simple update file containing invalid data, a null pointer logic error, crashed millions of Windows machines globally. Airports stopped. Hospitals canceled surgeries. Banks went offline, it was the same story as Ariane 5, a lack of rigorous testing for edge cases, and a system that was too fragile to handle bad input. Look at the cryptocurrency hacks, where bridges are drained of $600 million because of a rounding error or a reentrancy bug. The financial impact of software bugs is no longer limited to losing a document. It destroys economies. The lesson of the Ariane 5 is that software is no longer soft. It is hard infrastructure. It controls the brakes on your car. Toyota had a similar acceleration bug. It controls the pacemaker in your grandmother's chest. It controls the power grid that keeps your lights on. When you write code, you are defining the rules of reality for that system. And reality is unforgiving. There is a dangerous myth in tech that we are always moving forward, that new tools fix old problems. The truth is, technology accumulates. We build new layers on top of old layers. The banking system still runs on COBOL from the 70s. The internet runs on BGP protocols from the 80s. Your modern AI app runs on Python libraries that wrap C code from the 90s. If we don't understand, respect, and audit the layers beneath us, we are building skyscrapers on sand. The engineers at the ESA were not stupid. They were brilliant. They just stopped asking what if. They got comfortable. They assumed that the future would look like the past. They assumed that a variable called horizontal velocity would always behave the way it did yesterday. They stopped thinking like hackers and started thinking like bureaucrats. If you want to have a long, lucrative career in technology, you need to be the person who asks, what if? You need to be the person who understands the difference between a 16-bit integer and a 64-bit float. Even if you write in a high-level language like Python or JavaScript, you need to understand memory management. You need to understand how systems fail because they will fail. The goal isn't to build a system that never fails. That's impossible. The goal is to build a system that fails safely. A system that, when it encounters an error, doesn't steer the rocket into the ground, but instead resets, logs the error, and keeps flying. This deep understanding of systems is what separates the code monkeys from the engineers. A code monkey copies the solution. An engineer understands the problem. The market is flooded with people who can copy solutions. It is starving for people who understand problems. If you are tired of floating on the surface of technology, if you want to dive deep into the mechanics of how these systems actually work and how to break them, I have built a path for you. It is called the Hacker's Blueprint. It is not a generic coding boot. It is a 3-in-1 bundle designed to give you the dangerous competence that defines a true expert. It includes the Python Masterclass, but not just for... We teach automation, scripting, and how to control the environment your code runs in. It includes the Ethical Hacking Manual, because the only way to build a secure system is to know how to destroy it. You need to learn how to hunt for overflows, how to exploit logic errors, and how to think like the adversary. And it includes the cybersecurity protocol to give you the architectural view of networks and infrastructure. The Ariane 5 exploded because the engineers looked at the code but didn't see the danger. Don't make the same mistake with your career. Don't rely on legacy knowledge. Don't assume that what you learned yesterday is enough for tomorrow. Click the link in the description. Get the bundle. Start building your immunity to master the machine before the machine deletes you.